When solving problems using artificial intelligence, one common approach is to search through different possible actions to find a path from the start state to a goal state. One basic category of search methods is called uninformed search. These are strategies that do not have any extra information about how close a given state is to the goal. They only know the structure of the problem and what options are available from each state. Even without any additional knowledge, these search strategies can still find a solution, though they might not always do it in the most efficient way. Let's begin by understanding the idea of a search tree. Imagine you're trying to get from one city to another on a map. Each city is a node, and the roads connecting them are edges. The search tree represents all the paths you could possibly take, branching out from your starting point. The goal of search is to find a path through that tree that leads to your destination. One of the most basic uninformed search strategies is called breadth-first search, or BFS. Breadth-first search explores the search tree level by level. It starts at the root, which is the starting point, and explores all the possible actions from that point. Then it moves to the next level and explores all the new options from there, and so on. This strategy is guaranteed to find the shortest path to the goal if all steps have the same cost, because it always checks the shallowest nodes first. For example, imagine you're in a maze, and you explore every possible direction one step at a time before going further. That's how breadth-first search works. The downside is that it can use a lot of memory since it has to keep track of all the nodes it has discovered at each level. Next is depth-first search, or DFS. Depth-first search works by going as far down a path as it can before backtracking. Instead of exploring all immediate options first, it picks one direction and keeps going until it reaches the end or a dead end. If it doesn't find the goal, it goes back and tries the next path. DFS uses much less memory than BFS because it only needs to remember the path it's currently on. However, it has a risk. It can get stuck going down a very deep or even infinite path and miss shorter solutions that exist elsewhere. For example, if you're exploring a large maze and always take the leftmost path as far as you can, you might end up lost in a loop or dead end without ever checking the easier paths nearby. The third strategy is called Uniform Cost Search, or UCS. This method is a little smarter than BFS or DFS because it takes the cost of actions into account. Instead of exploring nodes in order of depth or position, UCS always picks the node with the lowest total cost from the starting point. It uses a priority queue to keep track of which node to expand next based on the cost. This means it's guaranteed to find the least expensive path to the goal, as long as all step costs are non-negative. For example, imagine you're trying to travel between cities where each road has a toll cost. UCS would help you find the cheapest route in terms of total tolls paid, not necessarily the shortest in distance or the quickest in time. To make this clearer, let's say you're trying to get from city A to city D. There are several paths, and each road between cities has a different cost. BFS would find the path with the fewest number of cities, regardless of cost. DFS might quickly find a path, but it might not be the best one. UCS would find the path with the lowest total cost, even if it means going through more cities, because it always chooses the cheapest overall route. All of these uninformed search methods are guaranteed to find a solution if one exists, but they differ in efficiency. BFS is complete and optimal when costs are equal, but it can be slow and memory-intensive. DFS is faster and uses less memory, but it might miss the best or even any solution if it gets stuck. UCS is both complete and optimal, even when costs vary, but it can be slow if there are many low-cost paths to explore before reaching the goal. In real-world applications, these uninformed search methods provide a foundation for understanding artificial intelligence techniques. Even though they don't use any knowledge about the goal's location, they show us how different strategies can affect the path we find and the resources we use.